I'm a mathematician. They're our counting numbers, and we always start counting at 0. So 0, 1, 2. In school you do this and you have rationals and reals and things, but we'll just put the integers for now. These are the things that we learn in school to add and multiply. We notice that there's not a biggest one. If I ask you, can you find a bigger integer than 100?
101.
101, excellent. How about 1,000,000?
1,000,001.
Pretty good. So for any n in the natural numbers, this is this blackboard boldface, that's its name, n. For n in n, there is, let's call it k, bigger than n. Agreed? You just added 1 to the numbers I gave you. You can always do that. But what about if we want a really big k? So what about a k bigger than n for all n? And so there's not anything in this list here of natural numbers, or our imagined list, that goes on forever. There's nothing there that's bigger than all the others, because you can always add 1. But I'm a model theorist. We don't just look at n, we look at other number systems. And there's one in which we have a k that's bigger than all of these. Out here, let's put in here. I'll call it n star. I'll just say it's another version of n. It has a lot of the same properties of n, but we can give ourselves a number out here which is bigger than all of these at once. So we're greedy, or we're lazy, or we say, why not? Because we're mathematicians. Of course, it's not bigger than itself, and it's not bigger than k plus 1. But for the ordinary natural numbers, it's bigger.
But it's still a natural number.
It's still a natural number, and so it has lots of the properties of natural numbers. Now, we can do this because we're model theorists and we use something called the compactness theorem. But there's a cost. We have to be careful what we can say and what we can't say. But we can say about these infinite integers, and there are more, I'll get to that in a second. We can say about these infinite integers whether they're even or odd, whether they're prime, whether they're squares. All of those are properties of ordinary natural numbers, and so you can ask it about your new and wonderful infinite ones.
So hang on, is this infinity?
They're all infinite. They're bigger than all of the finite numbers. But when people say the infinity, that's not what we're talking about. There are lots of kinds of infinity that the set theorists talk about. But even here, we're talking about just a nice, listable, countable thing with a lot of elements in it that are bigger than all the natural numbers. And if this were even, for example, what does it mean to be even? You say an integer is even if it's equal to twice another one? Yeah?
Yeah.
Well, then what about L? L is infinite too. It sits here somewhere. It's less than K, because K's double it. But it's out here. It's bigger than all of these.
If I start with K and start counting backwards, where am I going to end up?
You do it forever. K, K minus 1, K minus 2, K minus 1,000,000, all infinite.
And I'll never get back to that line that's got n on it?
No, never. Any more than you ever end here as you go up 1. Going up 1 never takes you a step at a time outside n. So there's something else going on that allows us to have K. Actually, I'm going to draw the number line now, the real numbers, let's say, or the rationals, it doesn't matter. So let's think about all the numbers like pi. Pi should be somewhere about here, right? Square root of 2 goes in here. So in school we learned this line, and all the real numbers. This have an ordering too, right? We have positive elements on the right, negative on the left. These have square roots, these don't. But we can think about the ordering and say, okay, I want something which is bigger than all the integers. Just mention the integers again, and here we go with K. It's out here. We can play the same game starting with the real numbers and get an infinite real number. And of course, it's got all its buddies. It's got a whole copy of this buddies, and more. Because what about now, before we divided by 2 if K was even? But in the real numbers, all the non-zero elements, and K is certainly non-zero, all the non-zero elements, you can take their reciprocals. You can divide by them. So what happens with 1 over K?
So this is almost like 1 divided by infinity almost.
It almost is. And so 1 over k, where does it fit in this line? Well, it's not out here. Actually, minus k is out here. You could think of that. It's beyond all the negatives, the regular ones. These are the ordinary reals. K is here. 1 over k is positive, and it fits infinitesimally close to 0, positive. So 1 over k is smaller than 1 over 3, 1 over 4, 1 over 5, 1 over n, and so forth.
It's just getting tighter and tighter into that 0.
It's an infinitesimal, which is something 19th century mathematicians and some current physicists like to have. It's infinitesimal. And so around 0, we have what I think some of the philosophers called a monad, which is a whole little interval of elements which are infinitely close. That's the monad, if you will. So they're all things like 1 over k, or in our earlier line, 1 over a half k.
1 over 2k, 1 over k.
All of those, they're all there. They're all in there.
If they're all infinitely close,
Yeah.
are they occupying the same space?
No. No, there's room. There's room. We just put them all in there, and they're in an order. Like 1 over k is going to be bigger than 1 over k squared, for example.
So 1 over k.
So the ordering out here is just flipped when you put it here.
So 1 over k squared is closer to the 0 than 1 over k.
Although they're both infinitely small, yes. One of the things that's fun to do, either with n or the reals, is a sort of thought of experiment, thinking, well, okay, are there infinite primes? Are there infinite integers that are the products of exactly 2 primes? Are there infinite integers that are powers of 2?